In this video, we're going to look at another example of using the graph of a given function to graph its derivative. In the last video, we discussed what the graph of the derivative contains. When we graph the derivative, what we're actually graphing is that we're graphing the instantaneous rates of change along the curvature of the given function that we have. And in the last video, what we saw was we had a point on our graph that came to this sharp little edge, or this cusp that we call it as. And we know that from class, cusps are not differentiable. The derivative doesn't exist at a cusp on our graph. And in order to kind of head that off at the pass for this video, when a graph is relatively smooth, when we see like this and it has a nice curvature to it with no bends or cusps or breaks, kind of jumps in the graph, we can assume that the graph is differentiable at all points along the curve. So what that means is when we graph f prime, the graph of f prime itself will also be continuous. So what we're going to do first is we're going to look at different slopes along the graph as we move from left to right and see how that correlates to the graph of our f prime. So as we start at the leftmost part of our graph here and move towards x equals -2, because x equals -2 is going to be an interesting value for us, namely because when we look there, we have a horizontal tangent. And when we have that, we know that our derivative is 0 and that our graph relates to a max or min of our original function. So we know that at x equals -2, there's something interesting going on. But everything to the left of -2, if we start down here, we see that we have very steep positive slopes, and as we gain closer and closer to -2, those slopes taper off, and they get less and less positive. We're still positive in our slope, but they're going to grow smaller and smaller until we finally hit a slope of 0 here. Okay, so let's go ahead and take that note down. So we have that left of x equals -2, we get positive slopes. That approach 0. Okay, and the next horizontal tangent value that we see maybe in question is actually x equals 0. When we look at x equals 0, we see that we have the same case of a horizontal tangent. Whereas with x equals -2, we saw that it was clearly a maximum. At x equals 0, we have a minimum, quote unquote. It's not really a minimum because it's not the smallest value it takes, but we can kind of associate it with that because the horizontal tangent that we have, or the derivative equaling 0, lets us know that something happens with a minimum or maximum in our graph. As we grow away from -2, the values of our slope become negative, but they start small. And as we grow closer to 1, they get steeper, but after we pass -1, they start tapering off again. They start going more and more approaching to 0. We have this flat one and this relatively flat one, but we have a steeper one as we get closer to -1. And as we go farther from -1 and go closer to 0, it starts to taper off again until it becomes 0. So how we can say that is between x equals -2 and x equals 0, negative slopes. And without getting too wordy in my writing, we remember what we talked about. We have negative slopes that grow more negative as we grow closer to -1. Then after we pass -1, they're going to become less negative and they're going to approach 0 again. So we have negative slopes between x equals -2 and x equals 0. But then, and as we move farther to the right from x equals 0, we see here that we start with a relatively flat kind of slope in the positive direction, but then as we move farther and farther right, we're also going to obtain steeper and steeper slopes to become more and more positive. So what that means is to the right of x equals 0, we get increasingly positive slopes. So that's what we have going on there. So what we just took down notes-wise is kind of the layout of what our derivative graph will be. So we already established that at x equals -2 and x equals 0, our derivative is 0. So we can go ahead and plot those points as negative 2, 0, and the origin, or 0, 0. But now let's talk about the notes that we took. So we said to the left of x equals negative 2, so anything this way, we're going to have positive slopes, so we're going to graph above the x-axis, but we're going to approach 0. So what that means is the slopes will continue in this way, but they'll grow closer to negative 2, or as they grow closer to negative 2, they'll become 0. And then we said between x equals negative 2 and 0, we noted that as we move from negative 2 to negative 1, we start flat, grow steeper, then after negative 1, we start steep, but then we taper off to flat again until we hit back to 0. So what that means is that our graph it'll be more negative, then as we hit 1, we start kind of going back on what we just did. We get steeper and steeper in the negative slopes, but then we start to taper back off after negative 1. And then we said to the right of x equals 0, we get positive slopes, but they keep increasing as we go farther from x equals 0. So this is what the graph of our derivative should look like.